I want to show you a typical output stage from a push-pull amplifier. At the heart of this circuit are a pair of pentodes, and they operate 180 degrees out of phase with each other across the primaries of this winding. Our high tension or B plus voltage from our power supply is connected here to the center tap of this transformer, and the large signal current is conducted to the plate. There is negligible voltage across this winding, and it might be 5 volts or so. So here I've indicated 360, 355 here. The pentode also has a screen grid here, and there are a number of ways that can be controlled, but in this design we're using a resistor, and the conditions at the screen, just like the conditions at the plate, determine how the pentode performs. So we have to take some care with that in the design. In this particular design, we're using a grounded cathode design. Like a MOSFET, where the voltage difference between the gate and the source controls the current through the device, the voltage difference between the cathode and the grid in this vacuum tube controls the current. But here's the difference. With a pentode, and vacuum tubes in general, the greater the difference, the less the current. The less the difference, the greater the current. A practical way to remember this is that if you lose your bias to a vacuum tube, say this wiper lifts on the pot, and you lose your bias, you're going to burn up your tube. In this design, we're using a type of bias, and it's called fixed bias. It's a bit confusing because fixed bias is almost adjustable through a pot. There's another way of biasing a pentode called cathode bias, and we'll look at that next. This drawing illustrates a typical topography known as cathode bias, and in this example we use a resistor here to elevate the voltage of the cathode a little bit, basically up to the operating point. And let's see, our operating point is 12 volts negative. We use this to raise the cathode to 12 volts positive and hold the grid at ground through a reference to ground anyway, through what's called a grid leak resistor here. And additionally, a capacitor is used right here to provide a better path to ground for the AC, small signal current, to hold that close to ground. You'll also notice here a coupling cap in this grid signal provided from the phase splitter. In this situation, the phase splitter is invariably going to be at a different voltage, usually quite high, DC-wise anyway. And we're trying to hold this grid at 0, so we put in a coupling cap here to block the DC. And you'll notice here that we've set up a high-pass filter. The RC relationship between that capacitor and that resistor is going to determine the break frequency of that high-pass filter. We want to pick a value for this capacitor and resistor combination that will allow us to pass most of the audible frequency, and we specifically do not want to pass frequencies we can't hear, because low frequency amplification will consume a great deal of power, and we don't want to waste that on frequencies we cannot hear. Typically I use 5 to 10 hertz. That's a nice wide band that allows you to pick a value of capacitor and resistor that will work well. In this particular circuit that we're using with this amplifier, I believe that's a 0.22 microfarad, and I believe the grid resistor is about maybe 200K.